Hey everyone, we're going to finish problem 26 and also take a quick look at problems 31 to 32. For part D, it says, can you tell us whether it would be unusual if the sample mean were greater than 2,800? Now the key word here is sample mean, right? Remember the population mean is 2631, standard deviation, population standard deviation is 500, but the sample standard deviation, remember, is only 50. So even without doing calculations, yes, we know that a sample mean being greater than 2,800 is unusual. In fact, it's flat out rare. Right? Because for two reasons. Number one, x is over 3 standard deviations above the mean. Actually, I should say above the mean for x bar, which is 2630. Remember, it's the same as the population mean. Further, since the sample size is greater than or equal to 30, we know that the sampling distribution is approximately normal. So it turns out that the probability that x bar is greater than 2,800, it winds up being very, very small. It winds up being approximately 0.0004 or 0.04%. Right, and if you do that in Minitab, you can just sort of see it right here, right? If we just kind of maybe crop this a little bit, right? So zoom in on that. All right, just sort of stick it right there. Okay, a little smaller. Okay, right there. So very, very tiny. Okay, now. On the other hand, do you think it'd be unusual for an individual apartment to have rent greater than 2,800? And the answer for that is no. Because we're not talking about the sample mean anymore. We're talking about a single apartment. So x greater than 2,800 is only at least how many standard deviations above the mean? Well, it's going to be the z-score, right, which is 2,800 minus 2631 all over 500, right? It's got to be 500, not 50, because we're talking about the population now. A single house or a single apartment. Right, and that winds up being what is the z-score for that? Right, let's see. Z-score for that 2,800 minus 2631 divided by 500, 0.338. Okay. Oh, nope, there. About 0.34. Right, which has area roughly, and then I think we've got a picture of this. I think it's, yeah, right there, about 0.3677, right, about 0.37. Oh, no. Roughly 0.37 under the curve. So 37% chance that a single apartment is greater than 2800, or 2800, yeah. So maybe I could say, so probability that x is greater than 2800 is roughly 0.37. Not so unusual, right? Okay. Next up, example 7, right? So we got 31, right? 500 book contains 250 sheets of paper, right? The population mean is 0.08. Population standard deviation is 0.01. Someone wants to know whether a randomly chosen page, singular, is more than 2 standard deviations above the mean. Can we compute the probability? Well, no, we cannot. Right? We know that it's somewhat unlikely to be 2 standard deviations above the mean in any distribution, right? Chebyshev's inequality. But we can't precisely calculate the probability. We don't know the distribution of the pages, or I should say of the page thickness. If it were approximately normal, then we would, right? Then we would be able to calculate it. But we don't know that. Or if we took a large sample of pages, if we took like a sample of 30 or more pages, then we could say, and then we could compute the probability that the sample mean is more than 0.1 millimeters thick. But for a single page, no, we cannot. And so similarly, an apple a day, right? A bag, right? A bag is supposed to weigh 10 pounds. You can view that as a population mean if you want. A 50-bag sample had mean weight of 10.3, standard deviation of 0.1. Someone wants to know the probability that a chosen bag, again, singular, weighs more than 10 pounds. No. Again, we don't know the distribution of bag weights. Right? If they had said that it was approximately normal, then we could. Or if they said, someone wants to know the probability that a randomly chosen sample of 50 bags weighs more than 10 pounds. Well, then we could talk about it. Right. But again, if we're talking about a single bag, we can't do it. And I'll just write here, and choosing a single bag, not a sample. All right, so all the sampling distribution stuff we learned doesn't apply.